Hello, welcome to this video. In this video, we will talk about vapor absorption refrigeration system. Now, we have already seen vapor compression refrigeration system where vapor is compressed, alright. Here we are talking about vapor absorption. So, that is the first difference which we will have to make. So, where vapor was compressed in vapor compression refrigeration system, here we are talking about absorption of vapor. So, it is a vapor absorption refrigeration system. A quick recall what we had discussed in our vapor compression refrigeration system is this. Let us say uh, we have some liquid, okay, which can boil at room temperature and pressure. Let us say ammonia can boil at minus 33.3 degrees Celsius. Okay. Now, that means if you use any refrigerant, the idea of cooling is if there is liquid and if it becomes vapor, all right, if it becomes vapor, it requires the amount of heat for uh, conversion of liquid to vapor, which we call it as latent heat of vaporization, all right. So, it absorbs that latent heat of vaporization from the surroundings, that is where we get the cooling. So, if you give me a liquid which can evaporate at room temperature and pressure, I can give you cooling. So, if this is liquid coming in and if it evaporates here, so that needs energy that is absorbed from the surrounding. So, the idea of vapor compression refrigeration system was this. For example, if we consider ammonia, the temperature at which this uh, is liquid is at minus 33.3 degrees Celsius. Now, if this is going to be at minus 33.3 degrees Celsius, it will be in liquid, all right. So, otherwise the other way of doing this is if you pressurize it, you can make it liquid. So, I pressurize the I pressurize this ammonia so that it becomes liquid. So, if you have this ammonia at liquid state at higher pressure, we can drop the pressure. So, then this gives me the cooling of minus 33.3 degrees Celsius. That is the idea, right. So, the whole process of vapor compression refrigeration system itself was making the refrigerant liquid and back into vapor. So, this was the idea. So, this was our evaporator and this pressurize we do it with respect to compressor, then condenser we had, then the pressure reducing throttling valve we had, alright. Now, let us move on. I mean, if you have liquid, you can get the cooling. That is the idea, right? So, Michael Faraday was conducting an experiment in around 1824, in the year 1824, and he was trying to liquefy certain gases. So, what he observed was there are certain materials which has more affinity towards some gases. For example, silver chloride powder had affinity towards ammonia gas, which means at room temperature and pressure, this was absorbing ammonia gas. So, forget about this burner for now and forget about the right side portion for now. Imagine that if you supply ammonia gas from here, this AgCl powder has the capacity to absorb it. Okay. Now, that is our first step. First step is ammonia gas is absorbed. Now, if we heat it, I mean to say that at different pressures and temperatures, this has less affinity towards ammonia. For example, if we heat this one, so I mean now we will stop this ammonia gas supply and open this valve so that whatever separates from here goes back here. Now, if we heat it, the ammonia in gaseous form again which is at higher pressure and temperature is gas, then it will have it will go to the other side of this experimental setup and where it is cooled. So, we have some cooling mechanism, maybe liquid water or something. So, if we cool this, now the ammonia gas which was separated can be liquefied. So, this was the idea. Now, what we have obtained is ammonia in its liquid form, ammonia in liquid form. Then what happened was he was fascinated by observing that this ammonia in liquid after certain time started evaporating and again it was absorbed by this AgCl powder. Now, if this starts evaporating, then obviously liquid to vaporization is happening here, that is evaporization, latent heat of vaporization has to be absorbed from here. So, this water was cooled. Now, this is what we wanted. So, this is the idea with which vapor absorption system is developed, all right. So, certain gases or materials will have a more affinity towards some gases at certain pressure and temperature, but less affinity at different pressures and temperature. Okay. Now, what we should do? Now, let us start from a point where we had discussed our vapor compression systems. Now, what was vapor compression systems was having? We had this condenser, we had this evaporator, then we had a throttling valve, right? So, a throttling valve. Okay. So, this is same in case of vapor absorption system as well. So, this is what we have condenser, and then we have evaporator here, and then we have a throttling valve here. Okay. Now, this side, if you recall, what was supposed to be here was compressor. So, we are replacing this portion, right side portion, the compressor is replaced by the different system. That is what we are discussing in a vapor absorption system. So, there has to be an absorber here. Now, what is the absorber's job is to? Now, absorber should have affinity towards this refrigerant, all right. So, this is an absorber. Now, absorber is in liquid state here, okay. Now, evaporator, whatever we are getting is a refrigerant in vapor state. So, here it is absorbed by this absorber. Now, let us say we are talking about the system which is water as an absorber, and ammonia as a refrigerant. Okay. Now, ammonia is absorbed by this absorber. Now, what do we mean by that? The ammonia as a refrigerant is coming from here at a vapor state. Now, it is absorbed by the absorber, that is water. Now, what we will have on the other side is a rich mixture. Now, what do we mean by rich mixture here? The mixture which has got uh, ammonia in liquid state as well as water. So, this is ammonia plus water coming from here. Now, since this is coming at lower pressure, now here also we will have lower pressure. Then since we are talking about the liquid system here, we will have to use a pump, all right. So, obviously, what should be received by condenser is this. Condenser should receive a gas or a vapor, that is only refrigerant we should get here, vapor which is at high pressure. That is what compressor was doing, right. High pressure vapor should be entering the condenser, then it liquefies it, but pressure will be high here, but throttling does the remaining process, dropping the pressure and giving you the evaporation process. Now, pump should increase the pressure, okay. So, once the pressure is increased, now what should be next? Next we should have an absorber, okay. Now, what is a generator, all right. Next, what should we have is a generator. Now, what should generator do? Generator should be supplied with heat, okay. So, let us call it as QG, so that only ammonia is separated. Now, ammonia obviously again back in gaseous state here, okay. Ammonia in gaseous state will be separated here. Then this will have, now this will be weak. I mean, even though it may have ammonia gas, but this will be weak. So, we can call it as, we will have it as weak solution coming out from here. So, this will send it back to absorber, all right. So, that, so it should not be an infinite loop, right. So, it has to go back here, otherwise what we will have is we will end up, that absorber will no longer have the solution at all. So, this has to be sent back, but we should reduce the pressure because the generator pressure will be higher. So, let us reduce the pressure before we send it to here. So, and it can also be like sprayed here, all right. Now, This was supposed to be coming to here. Now remember, generator is the ammonia which is separated from here, which is in gaseous state, may have some water vapor present here. So let us have a rectifier. Now rectifier's job is to, if there is any water vapor present here, we don't want this to go through the condensation process. It may freeze otherwise. So we will separate the water vapor in the rectifier and send it back to the generator. All right. Then we can also have a performance improving device, that is a heat exchanger between here and here, because anyhow after pumping we are going to supply the heat and generate in the generator. So instead of wasting the heat here, let us have a heat exchanger, so that this gets up, I mean this will have a heat exchanger. So before going to the absorber, it gives away some of its heat to the rich mixture which is coming from here. All right. So this is our vapor absorption refrigeration system. Okay. Now we can also write condenser, I mean energy balance we will try to do. So condenser should be rejecting heat to the atmosphere, let us call that as QC, and the temperature at which this rejects the heat to the atmosphere is called as TA. Now evaporator should absorb the heat, evaporator should absorb the heat. Okay. So let us say that is happening with an amount of QE, and the temperature at that is happening is TE. And remember, generator is supplied with QG, and the temperature, let us say that it is temperature TG. And similarly, absorber should be also rejecting heat at QA, and temperature at this happens is called as TA. And of course, we need to supply work or energy to the pump. Okay, this is our water ammonia vapor absorption refrigeration system. Okay, the same thing is depicted here. Okay, the left side portion which we already know, this is same in vapor compression refrigeration as well. Now this is our rectifier. Okay, now we have this absorber where this is water. Now this is coming from here is ammonia. Okay, ammonia in vapor state, of course. Now that is absorbed in this absorber. Then we have a rich solution where we pump it back to the generator, where we supply the heat in the generator, and then we end up with getting the high pressure ammonia. Then that is condensed back, and this cycle continues. All right. Now let us derive COP for this vapor absorption refrigeration system. Okay. Vapor absorption refrigeration system. Now let us do the energy balance. Now what is the equation for COP, by the way? Now COP is desired output. Now desired output divided by input. Now what is desired output in a refrigerator? So heat to be removed from the evaporator is the desired output. So QE is desired, and the input which we are giving is one is WP, and the other one is we are also supplying heat in the generator. So unlike a vapor compression refrigeration system where electricity is the main source of energy for running a compressor, here we have QG, all right, and also there is small amount of energy which is spent on pump. So this is our equation. So let us call this as equation 1. Okay. Now let us do the energy balance by looking at the diagram. Now what is the energy balance here? We have energy rejected must be equal to energy absorbed or energy given, all right, energy given. Now energy rejected can be seen from condenser and absorber, right. So QA plus QC. So these are the two forms of energy which is going out, and energy given or energy absorbed by the refrigerant will be, we have QE that is evaporator energy, plus Qg, that is energy given to the generator, and then we have Wp, which is the work given to the pump. Call this as equation. Okay. Now call this as equation 2. Now we know for minimum or maximum COP, we can say for maximum COP, the cyclic integral of this delta Q by T, that is change in entropy, cyclic integral of entropy or delta Q by T must be equal to this. So, I will try to write it this in terms of divided by temperature. Now, corresponding temperature we will write first, I mean equation 2 with corresponding temperature. I will divide them, divide equation 2 by corresponding temperature. All right. If we divide this by corresponding temperature, we know that QA, that is happening with respect to temperature of atmosphere. Even QC, if you see, that is also happening with condenser is rejecting to atmospheric temperature. So, instead of this, I can write QA plus QC by TA. All right, that is also fine. QA plus QC by TA. QC by TA condenser. All right. Now, QE, that is evaporator temperature, is TE, and this can be written as QG plus WB divided by generator temperature. Let us call this the equation 3. Now, I can rewrite this same equation 2. Now, equation 2 divide whole equation, let us divide by T suffix A. I mean, I am dividing the whole equation by TA. Now, that will be QA plus QC by TA, that is on the left side, and right side you can be QE by TA plus QG plus WP by TA. Same equation 2 is divided by TA. Now, we can compare equation 3 and 4. Okay. Compare equation 3 and equation 4. LHS is same. So, I can rewrite. So, RHS of this must be equal to RHS of this. I mean to say QE by TE plus QG plus WT by TG must be equal to QE by TA plus QG plus WP by TA. All right. Now, I will try to separate the similar terms QE by TA on the left side. I will send this QE by TA also to the left side. Then we will have this QG plus WP common, or if we can take one more step, that is also fine, QG plus WP by TG. Now, here I can take QG as common, we will have 1 by TE minus 1 by TA. Okay. This QE as common. So, 1 by T minus 1 by T. So, similarly here I can take QG plus W as common, and I will have 1 by TA minus 1 by TG. Okay. Now, I will keep it in the form of QE divided by QG plus WP. Remember, this is nothing but COP, right? Now, COP is what? Equation 1, QE by QG plus WP. So, then the remaining terms 1 by TA minus 1 by TG divided by, this will go here, 1 by TE minus 1 by TA. Okay. Now, this can be further written as TG minus TA divided by TA TG divided by TA minus TE divided by TA TE. Now, TA TA cancels out. We can say that this will be TG minus TA by TG. Okay. And this will go here as TE divided by TA minus TE, and that is what COP is, right. So, therefore, COP of a vapor absorption refrigeration system can be given by, because this itself is COP, right? Desired output by input. So, Tg minus Ta divided by Tg, that is, if you know all the temperatures, that is generator temperature, ambient temperature and evaporator temperature, we can determine the COP. Okay. We will continue in the next class. Thank you.